Hello everybody, and welcome to my video on the binomial distribution and some applications. Alright, so the binomial distribution, in order to have it, you have to check 4 boxes. That is, you need to have n identical trials. You need each trial to be independent from the rest of the trials. You need to have 2 outcomes that are marked as success or failure. And you need a probability of success and fail to be fixed from trial to trial. All right, let's jump right into this for my examples. I have 3 examples I want to work through. We'll do one, we'll pause, let you try the second, we'll pause, let you try the third. So right off the gate, let's look at example 1. We want to study the next 4 customers into a store. The typical shopper will buy 30% of the time. How do we know this? Trend data. So the first question, part A, do we know it's binomial? Well, if it's binomial, it has to go through each one of the checkpoints. So the quick one I look for is, do I have a fixed number, an n number of trials? In this case, n equals 4 for the customers. We have 4 customers coming into the store. Got it. So that's one of the key ingredients. Second, I need a fixed percent of success. Well, I should start then with what is a success. A success is they will buy. Customer will buy. A customer will either buy the product or not buy the product when they're in the store. So far we got 2 out of the 4 checks. We got an N, we have a success. We also have our pi. Now, the way I've been taught, utilizing most of the statistics books I know, they utilize capital pi to be the probability of success in a population. In this case, capital pi will be 0.3 as given in the data. This is a reliable source that typically over time 30% of our shoppers buy the product. So we have our N, our pi, and success is customers will buy. So we got 3 out of the 4 things that make it binomial. The 4th is all about randomness. Well, when we look at the next 4 customers in the store, I don't believe one customer's buying habits will influence another customer's buying habits. If you do believe in that, what you could do is instead do a sample of 4 random customers in the store to really highlight the need for the binomial. I often love the word random because that really gives me that independence from one trial to another. I'm going to assume independence here because I don't see how one shopper, the next 4 customers, have anything to do with each other as they come into the store. So independence by the shoppers. All right, so we have our 4 ingredients to say, yes, we definitely do have a binomial distribution. We should always check to ensure that we have a binomial distribution or any of these other distributions I'm going to talk about in later videos. All right, now that we have the fact that it's a binomial distribution and it's our first example, the way I want to tackle part B is via the formula. What do I mean by that? Let's talk about it. So WITP, what is the probability for each and every outcome and build a table? What do I mean by outcome? Well, we're studying 4 customers. So when we study 4 customers, and X is the number of success or the number of buyers, we'll call them, because we have all the customers. We don't know if they're buying or not. We can go through all the options. All 4 customers could come in. None of them buys the product. 1 of them buys the product. 2 of them buy the product. 3 of them buy the product. Or we get lucky and we go 4 for 4. All 4 customers buy the product. So we know what X is, the number of buyers. We have N. We have pi. These 3 pieces, N, pi, and X, are the key ingredients to how I will form the probability. And how do I do that? Or how does one do that? Well, you can look up the formula for binomial. The formula for binomial distribution is right here. Yes, I know Excel has a quick trick. Let's not go there yet. Let's look at the binomial distribution and what it means. Well, let's look at an example here. What we're looking for here is, what are the odds we're going to see 4 customers come in the store and not a single one buy the product? So here's what happens. I think of it as buckets. I actually have 4 buckets here, right? I have 4 customers. I have customer 1, customer 2, customer 3, customer 4. All 4 of them say no, they don't want to buy the product. And each one of them has a 30% chance of buying the product. So if they're not buying a product, that's like each one of them individually saying 70% chance, no, 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 no. And so because they're independent, we have a rule in probability that we can multiply the odds of all of these together. So what I see over here for the probability of all of them saying no is just 0.7 raised to the fourth. And so that's our answer. And I'll do it in the next column nicely, neatly. I'll do it the neat probability here. I want to do the dirty work with you and show you how you could build it by hand if you'd like. And then, yes, we'll utilize Excel to make it quick. But right now, I want you to think about why it's binomial. That's the main thing, is how do we know this scenario is binomial? Because we satisfied these 4 ingredients. Now, let's walk through how we could build the probability distribution. So that's the odds of getting 0 buyers out of 4 shoppers right there. Those are the odds. 70% times 70% times 70 times 70. The keyword was independent. Allow me to multiply them together like that. All right, let's go to here. So one person buys a product. Woohoo, 30% chance. The rest of them say no. They don't want the product, and that's why the 70s. So what I see here is I do see a 0.3 one time, and I see a 0.7 3 times. And so what I see is one person said yes, 3 people said no. I'm trying to develop a little algorithm here. But there's a slight little issue in my formula. Why? Think about it. Why did the first customer say yes? Why couldn't any of the other people say yes? And they could have. So this number could have rotated to this person or this person or this person. In some respects, you could say of these 4, choose 1 to say yes. And so I'm going to augment this formula by 4. I'm going to choose 1 person to say yes. And because of this, let me put that up here. Let me augment this to give you a little taste here of what I'm going at. Let's say the 0.3, there was nobody wanted to say yes. 4 people wanted to say no. And 4 of the 4, how can we choose all of them or none of them to buy? What I'm trying to come up with is a pattern. Binomial distributions have a nice, sweet pattern. All right, let's go down to this. Right here, 4. All 4 customers. So that means all 4 customers say yes. That's pretty easy, right? All 4 customers say yes. How many ways can all 4 say yes? Only one way, this way. It's really easy to do the endpoints of the binomial because it's either all no or all yes, all fail or all success. This 4 for 4 would be all success. So I see all 4 people saying yes and not a single person saying no. And I still got to understand, how many ways can I choose 4 for 4? How can I go 4 for 4? Because that's what I want. I want all 4 customers to say yes. All right, let's back it up one. And I'm pausing, starting to pause a little bit to give you a chance to stay with me, to stay on top of me and try to fill out what I'm going to do. So here, in this case, 3 people say yes. What that tells me, 3 people say yes, I want it. Yes, I want it. And 1 person says, no, I will not buy the product. So once again, I see, because of independence, I got 0.3, I'm multiplying 3 times. I got a 0.7 for the 1 person that said no. And think about this. Of the 4 people, we want to choose 3 of our closest friends to do it. Or the other way to look at it is there's 1 person that says no. And so you can think of it and the complement, 1 person out of the 4 has to say no. All right, but I rather see it as positive. Of the 4, I want to choose 3 that are going to say yes. And you could be the first 2 say yes and the 4th. The first 3 say yes and the 4th. The first and 1, 3, and 4 say yes. 1, and you can go through all the combinations, all the choosings of who can say 3 people saying yes out of 4. Just write it down. Mary, Sally, Ted, Bob. Write down how many ways can you pick 3 out of 4, and it'll be 4 choose 3. That's the definition of 4 choose 3. All right, let's look at the one in the middle. Usually it's the toughest one. That's why I save it to the end. I got two people saying yes, two people saying no. And so if you look at the pattern, just look at the pattern there. If this was an SAT question, what would be the exponent in this pattern? 2, right? Look at the pattern. Look at the pattern. There's a clear pattern, and that's the reason why binomials are easy to deal with. And yes, we have 4 people, and I want to choose 2 to buy the product. That's really what's going to happen. 2 people will buy the product. Could be the first 2, could be the first and third, could be first and fourth, could be second and third, second and fourth, could be third and fourth. And I believe those are all the iterations of that. I'd have to write it down to be careful myself. That's what choose deals with is 4 friends, choose 2. 4 friends, choose 3. And that's really the argument why what I'm going to write this with just an equals, why the formula here makes sense. This is just another way of writing choose with factorials, okay? This is nothing more than n choose x. With probability of success, x times, and 1 minus probability, so probability of not a success, the failure, and minus x times. And that's really all I did each and every way. So the example I'm doing is just a simplistic way to show you this formula works. All right, so if you want to do it by formula, you can. You just got to know n, sample size, how many times you're running the trials, x, number of successes you want, pi, probability of success. Good news, those 3 things are part of the definition of binomial. You should be able to write down n, x, and pi if you're going to do a binomial distribution. So all these numbers plugged in, and you get your answer. And that's why I was able to fill this out. I got my x, I got my n, I got my pi. And I just filled in the formula on the formula sheet. All right, let's do this in Excel. So first, we want 4 choose 0. So I believe there's a choose function. And all right, guys. So I want to neaten this up a little bit. So I want to neaten this up by saying, okay, let's do the choose first, because that's the first part of the formula for probability by binomial. So the choose, wrong choose, I apologize, combination. So combination will be a great formula for building combination. And I like to pause and read every time I see Excel, in case they have a new version of Excel, if they change the formula. It says number and number chosen. Got it. So they want n and they want x. So I want, of the 4, I want to choose nobody. By the way, that's 1, because how many ways can you choose nobody out of 4? Only 1 way. I choose nobody. Times, and then I'm going to write the rest in. 0.3 raised to the 0 times, can't type, sorry guys, I don't need parentheses, 0.7 raised to the 4. And we get, there's the odds of all 4 customers saying no, 24%. That's the odds of all 4 customers saying no, 24% chance. Okay, so we move down. So I'm just going to copy this down and tweak it as needed. All right, so now I have 4. I want to choose 1. That means 1 person bought it, 3 people did not. Let's see what happens. Wow, it goes up to 41%. So there's a 41% chance I get 1 customer out of 4 to buy the product. Interesting. All right, let's see what happens when we have the odds of 2 customers. What are the odds that exactly 2 customers buy the product? Because that's what we're finding right now. The odds of exactly 2 customers, 26%. Okay, what are the odds exactly 3 customers buy the product? So I want 3 customers to buy the product, 1 customer not to buy the product. And that odd goes down again. That makes sense. And the odds that all 4 buy the product should be very, very slim. The odds that all 4 buy the product should be extremely thin, and it is. Now, I like to make sure it is a distribution from my previous video. Hopefully you're watching these videos in order, and you'll notice whenever it's a distribution, and binomial is a general distribution, a general discrete distribution, it still holds true to the rule that all the probabilities in the end have to add to 1. And I'm happy there. That means I have got all options laid out on the table. Nothing's hidden. Think about it. 4 customers, what could happen? Nobody buys it, one customer buys it, two customer buys it, three customer buys it, four customer buys it, 4 for 4. What are their odds? And here they are. How did I find these odds? I needed to know this was a binomial distribution. Luck would have it, I have rules for why it's binomial. By knowing it's a binomial distribution, I jumped right into the ability of using the binomial formula. Now, of course, once you have the distribution, you can come up with the next question that I asked you to do. Part C, what is the expected number of shoppers? So what is the expected number? I see 4 customers come in. What's the expected? Another group of 4, another group of 4. What's expected in a group of 4 to buy? Well, recall from our previous video, expectation, what you would do is sum the X times P column. The X being the outcome times the probability of that outcome, the XP column, for each one down. Adding that up gives you the expectation. So here is the average number of buyers. I expect in groups of 4, 1.2 buyers. So what I would do in my data set, here's 4 random customers, 2 bought it, got it. Here's another 4 random customers, 3 bought, got it. Here's another, I'm thinking about collecting this data in Excel, and I'm just listing, all right, I'm watching them. Here's 4 customers, 2 people bought the product. Here's another 4 customers, 1 person bought it. Here's another 4 customers, 4 people bought it. Here's another 4 customers, and I just watch all day long, random 4 customers. The idea of average means if I do this in a long study and I find the average, it would be 1.2. The average of these numbers, if I follow true to this probability distribution, that is 41% of the time I better see a 1, 52% of the time I better see a 2. All right, so if I'm holding true to the probability distribution, sorry, that's not the probability distribution. I apologize. Here it is. All right, got the wrong thing. The probability distribution, 24 out of 100 times, I better see a 0. 41 out of 100 times, I better see a 1, so on and so forth. So typically, when I run my trials, I should see this type of distribution of 2s, 1s, 0s, and 4s, so on and so forth. So that's what the 1.2 means. The cool thing, the really cool thing, is if it's binomial, you can actually, in advanced statistics, you can show the average. That's the cool thing about, here's the thing. If it's discrete, this always works. If you have your X and P column, you have your outcomes and your probability. If you create an outcomes times probability column and add it up, you'll always get the average. Please watch my video on discrete variables to see this in action. But a binomial distribution is just a very special one, the VIP section of the discrete variables. Since it's VIP, we actually can find the mean and standard deviation without building some tables. We could, if we want, build the tables, nothing wrong with that. And with Excel, not hard to do. Or we can find the mean by a good old straight up formula that we memorize in binomial. If it's a binomial distribution, then the average is nothing more than n times pi. Look how quickly that is. The average is nothing more than n times pi. Well, all right, guys, let's check that out. All right, the average was supposed to be n, and n in this case is 4 customers, times pi. Pi in this case is 0.3. Boom. And look at that. It matches, whether you do it by the table or whether you do it by the formula. Your choice, really. It all depends on how you attack these problems in general. All right, you have the discrete distribution, but you have some fancy discretes, the binomial and the Poisson and the hypergeometric. Each one of these 3 in my videos, I'll show you how you can get quick answers to them. Poisson and hypergeometric are coming later. We're focusing on the binomial today. Excellent. All right, now that I've done our example 1, please pause the video and see if you can attack example 2 before I give you the answers. All right, we studied 300 random students of the local school to research autism levels. It is reported that a typical school district will have 14% of its population with an autism characteristic. Okay, first and foremost, it's got to be binomial for me to attack it with a binomial distribution. So how do we check that out? Well, first, we have to have n. And yes, we are going to look at 300 students. We need to know a success. Well, success in this case is child with autism or autistic characteristics. So what else do we need? We need pi, a fixed percent. Well, many studies have been done, and a fixed percent in this case is 14%. Last but not least, I said I'm going to do random students, and random implies we have independence. And independence is needed for me to utilize these quick trick multiplication tricks I did up in example 1. So yes, it is a binomial distribution. No issues. Awesome. So then the rest of these, I'm going to let you know, I'm going to go straight to the quick tricks. I can utilize the neat probabilities and the rules. What do I mean by that? Well, let's look at part B. Exactly 39. So here's the thing. I'm thinking about the fact that I am in a combination. Total number, there's 300 of them, and I'm choosing 39 to have it, okay? Think about that. Of the 300, I'm choosing 39 to have it. Which 39? Don't know, don't care. Combination will give me all the patterns of that. Now we're going to multiply by, let's think about this now. So probability of success is 14%. How many do we want the successful characteristic in this case? 39. Got it. So that, first of all, leads to the odds of not a success, 86%. Why does that? Think about that. The answer is simple. The two numbers in the parentheses have to add to 100% because we have success and failure, and those are the only two options, hence the binomial. All right, if 39 have the characteristic you want, then the rest can't. And so 200 minus 39, I believe, is 261. The little thing I keep in mind is these two add to 100%, these two add to n. So 39 and 261 add to 300. Boom, and there's my answer. There's a 6% chance that exactly when I do my study, 39 students have the autism in this study. All right, it's fun. I love it. I love building it like this, but it's kind of tedious. The good news, this formula that you see up here, the formula you see up here, which is the formula for binomial, is tucked nicely in the binom.dist function. Think about it. What letters do you need? X, N, P or pi. I use P, but pi is the letter. And cumulative. So this is the only thing we have to think about is what does this mean? Well, let's look at it. So if we're going to do it by Excel, equals binom.dist. So number of successes. Well, we want 39 people in this study. How many trials are we running? 300. What's the probability you see somebody with that characteristic? 14%. This is very important. You need to know if you're looking at the characteristic or not. That's very important to binomial. You need to know if you're putting in 0.14 or 0.86. You got to be careful. Last but not least, binom.dist will count down. We'll talk about that later. In this case, I'm going to put a 0 for the false command. That's what it means. I don't want to use the cumulative distribution. I just want the probability of mass. What that means is I just want it to be the 39th person and not anymore. I want to pick exactly 39. That'll be important to me. We'll see further when you see questions of less than and more than. We'll get right to that. All right. So let's speed this up now. Part C. I want exactly 90. So again, do it by hand again. Of course, it's a combination. How many ways are you going to be able to take from 300? You're going to choose 90 people. How many ways can that be done? A lot, obviously. Now, to come up with the binomial distribution, we have to know the number of successes. We have them, exactly 90. 14% of them will have 90. I just think about the buckets I drew up earlier in example 1. In example 2, I'd have 300 buckets. 90 of them would have a yes for the autism characteristic. Yep, that was right. And then we'd have not 90, but 210 of them, 210 of the buckets with the no characteristic. At any time, please pause the video and make sure everything makes sense. I'm going to check this. First of all, that is a really, really small number. That's one thing to note before I move on. When you see e to the negative 13, what that really represents is a decimal shift left 13 units. That's really what it means. It's multiplied by 10 times to the negative 13th power. A very, very small number. Might as well call it 0. Okay, so how can we use Excel? Well, Excel, binomial.dist, says, how many successes do you want? We want exactly 90 people in my study. How many people are studying? 300. What are the odds of success each and every time? 14%. Again, I can't repeat enough. All three of these numbers should be clear. The last one you got to think about. Are you sure you want exactly? The answer is yes. Whenever I want exactly, I put a 0. And notice they match. Awesome. So what's next? Well, now we ask questions, what are the odds that less than 50 people? So that's important to me. So part D, here's what I'm going to work on, sets. I like to think about what are my solution sets. It really helps me build my binom.dist. So in part D, we want less than 50 students. Less than 50 students. To me, that would be 49, 48, dot, 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 2, 1, and 0. It'd be that whole set, right? That would be the people less than 50. Now, I could do this by doing the binom dist for each and every one of them. Obviously, that would be 50 times I got to do it. Wow. So what's the best way to attack this problem? The best way to attack this problem is the binom.dist now and use the fourth identity here, the cumulative. What you can do is if you put a 1, notice in the previous two, B and C, I want it exactly. Exactly means I don't want to count down. I want exactly 39, and that's why I put a 0 in there. I want exactly 90, and that's why the fourth element was 0. When I want less than, I want it to count down. Notice my set is 49 down to 0. So 49 is the first number in my set out of the 300, probability of success, 0.14, and I want it to count down. The cumulative will count down. And so what that 1 does, it turns on the counter of Excel, and it will count down from 49 down to 0. The countdown being it'll run the binom.dist for each and every one of them and add it together. And just like that, I have an easy answer, 89% chance. And then we can think about that more. We can think about what that means for my study, right? For part D, what are the odds we see less than 50? 89% chance. All right, it's a really overwhelming odds it should happen. And that's very important because when you do these studies, you want to know if you're hitting the mark or missing the mark. All right, what is the probability that more than 80 students, more than, all right, set equals more than, all right, more than 80. So that means we are counting down from 300. I always count down 300, 299, dot, dot, dot. And we get down to more than 80, so 81. We will not get to 80 because we want to be more than 80. Welcome to the English language. You gotta be careful. All right, so I want to run this. All right, here's the key. There's really 3 things to know: how to do exactly, how to do less than, and how to do more than. You understand those 3, you're good to go in these distributions. Exactly we did. Less than we did, we just put on the 1. The more than, well, we worked about this in the general distribution. The more than is opposite of the less than. That's a great thing about the binomial distribution. So you think about it, the more than is 1 minus the less than. So if we do 1 minus because it's the less than, and then we attack with the less than, we'll get the answer of the more than. Let me explain that very clear. I want 381. That's what I want, because again, the question was more than 80. So I want to add up the probabilities of each and every one of these individually. So what I'm going to do instead is I'm going to add up the complement, 80 and down. See, Excel does down very well. You'll see this a lot. To the left, it'll do to the left or count down very nicely. The numbers in the middle usually don't change. So what I've written here is the binom.dist. I'm going to calculate 80 and down. Start counting with 80, 79, so on and so forth. These are actually the bad answers, right? Though 80 to 0 is the bad answers because I want 381. 80 to 0, the bad answers. Once I know that probability of 80 to 0, and that's what the 1 will do, count down, I know the answer I want is 1 minus. That's why we often say a more than is a 1 minus solution. And there's our answer. Again, a very small odds of this happening. It is a very small odds of part E happening. More than 80 people report. So if I do this report and I do get more than 80, I get 82 people report, I know something's unusual in this school district. Or my report's wrong, or somebody's lying. There's so many things to look at. But it raises a red flag. Look at the odds of more than 80 reporting. Almost zero. So if that happens, we have to look at the school district a little bit more. All right, let's continue. Part F, at least 35 students. Well, at least is another way of saying more than. That's why I always build my set. It helps me. More, at least 35. At least 35. That's 300, 299, dot, 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 all the way down to 35 and including 35. The English language is beautiful, but you got to be careful. More than does not include the lower number. At least does include the lower number. Just got to get used to the English language. All right, since this set counts down from the cap, then I know it's a more than question, so my answer will once again 1 minus. And what I'll do with the binomial dist, which does very well, is once again, it counts down. Binomial dist counts down very well. The algorithm is to count down. So I want to count down from 34. Why not 35? Because 35 is the good set. 35 is in the set. If I'm doing 1 minus, whenever I do a minus, I think about the ones I don't want. That's really what this is 1 minus. What is the first one I don't want? If this is the numbers I want, the first number I don't want is 34. And that's how I get that number. There's a lot of set theory topics we could discuss here. Did I get the right number? I apologize. And a 1, because I want to count down. So again, binomial dist counts down when you turn on the counter of a 1. And so that goes from 34, counts down to 0. That's the numbers I don't want. These are the numbers we want. So 1 minus gives me the total answer using complements. And there we go. Again, a very high chance. There's a very high chance we're going to see at least 35 students that report. A very high chance. Excellent. All right. Expected. Well, to do expected, you could build the table out. That's true. You could build the table, but because it's binomial, and that's the key. That's why this check is so gosh darn important right there. That check is saving my life. That is binomial. Since it's binomial, I can either recall or look it up. The binomial distribution has a mean, and by the way, the standard deviation of quick formulas. You just need n and pi. So the mean for a, so this is just n times pi. So the answer here is, think about it though, 300 kids were studying, and there's a 14% chance each time. So you'd think you would just multiply the 2. And there you go. I would think on average 42 kids per school district. If I grab 300 random kids, I should see 42 with autistic characteristics. If I see too many off of that center, I might think we have an unusual set of circumstances. For example, what we did here. 81 is a little too far from our center, right? Our expected. And that's why we like our expected. This is our mean, what we expect to come out. Well, the mean means nothing without the spread. And that's why usually now you do the spread next, the standard deviation. Well, the standard deviation, again, is a formula. So I'm just going to type this formula in. The formula is the square root, that's what it is, the square root of n, what's our n in this case, 300, times probability of success, which is 14, times the probability of a not success, which is 0.86. So that's the formula. Let me leave it there again. Let me check on it again. It is square root of n pi 1 minus pi, the complement. And that's what I wrote there, n pi 1 minus pi, square rooted. Why are these formulas true? Go look them up. These are not, those ideas are not in this video. So what we have here, though, is 42 students typically in a group of 300 students will have the autism characteristic with a typical spread between groups of 6. So when I grab another 300 students, plus or minus 6 per group is a typical spread per group. So I have one group, blah, and the other group blah, the number of kids with autism characteristics will be separated by about 6 typically per group. I want to make that clear what that spread tells me. It's a spread per group. And this all comes about. G and H are huge to me. Center and spread, always the key to me. You tell me center, you tell me spread, I can tell you I, which is what's unusual. Well, unusual is usually, so part I, what's unusual? Unusual, can't spell today. What am I saying? I can't spell any time. Unusual is usually 2 standard deviations from average. That's typical. 2 standard deviations from average is typically unusual. Every professor is different. This is just the way I start. There are some higher level ways of looking at unusual, okay? You can go to binomial tables, so on and so forth. I look at it in general, 2 standard deviations away is unusual. So let's think about this. What would it mean to be a low unusual value, a low number of people with the autism characteristic? Well, that's typical, 42, minus twice. Why? Twice what? Twice the spread factor. Again, per each group, I expect 6 students difference. If more than double that, so twice that, why twice? You'll get into that later when we talk about normal. Twice is usually the endpoint that we use for outliers, unusual values. And so 29.98 would be a low bound for outlier to me. If you get 29, so roughly 30, less than 30 kids. If you see less than 30 kids with autism, I really want to know what's going on in the school district, what's unique about the school district, because they're a little farther from the average than typical. Now, one way you can look at it is maybe that number is wrong, right? This number we got from a report is wrong and it's no longer 14%. All right, you always got to make sure that this number is true. But if that's true, and this is truly the center, and this is truly the spread per group, if I see a group of 300 with 30 or less, I'm really, really interested in that school district because they're too far from average. Again, we're averaging 42 kids per group, plus or minus 6, all right? So double that, 6, you get 12. I'm allowed to go 12 lower and 12 higher than this. Anything more than that is unusual. And that's why I write the center plus 12, or 2 times 6, is the high bound for outlier. So if I see more than 54 students with autism, I really am curious because the odds of that would be really, really high. The odds of seeing outside of that 2 standard deviations, and that's why you really got to understand the mean and the standard deviation to really understand how I got this. The mean is the center of your distribution, where typically you're going to see it when you do enough of this activity. You should most of the time see 42 students, plus or minus each group of about 6. So you can see 43 one group, 38 another group, no big deal. As long as you're within 6, no problem. As long as you're within 12, really, really no problem. So we double this number, all right? We double this number. That gets you to about 30, and that's why the low bound's around 30. You double this number, you get about 12 again. You add to that, you get about 54. These are the rough bounds on outliers right there. And that's really the key to all of this. We know it's binomial. So when we do the study, we have ideas of what the outcomes are going to be. If the outcomes don't match, now we have something significant to talk about in the school district, and that's what it's all about. It's not about the numbers. To me it is. I love the numbers. But it's also why. Why do we do the binomial distribution? Well, we do the binomial because it helps me come up with what's unusual in this school district. Excellent. So I know it's a long video. Keep with me. One more example. We'll kind of flow through it real fast. I'm going to put a pause on it here, let you flow with it, and I'll be right back. Alrighty, we're back for number 3. Let's do this fast and furious. Part A. And pause at any time to make sure. It's a binomial distribution. Let's check this out. Do we have n, a fixed number of channels? We do. 120 random shoppers. In fact, let me just jump into, I like to keep it in order. N pi. What's the probability of success? 48%. Got it. What is a success here? A success here is a buyer again. Got it. A person will buy the phone 48% of the time. No problem. And pi, success. Random. Oh, yeah, we got random shoppers. That implies we definitely have independence. Independence is a key word when you're doing probability distributions. Oh, yeah, we have the binomial distribution. Again, why do we care about this? Because if not, I'm building a table like we did in the discrete distributions with over 120 rows of information to calculate it out. Thank you for knowing it's binomial. Because now we can answer important questions like, what is the probability exactly 62 shoppers buy the phone? Let's say we need that number to make our promotion, to make our cutoff, all right, to make our quota. What are the odds of this happening today? What is the odds today? We got 120 shoppers coming in. 62 are going to buy the phone. We need this or we're not going to hit the quota. Well, let's check it out, my friends. Binom.dis. What are the odds we're going to make our quota here? Well, we want 62 people to buy the phone. We have 120 people shopping. The probability of success is 50-50, might as well say 48%. Now comes the big clutch moment for you guys. 0-1, people. 0-1. Well, in this case, it's 0 because we're looking at exactly 62 shoppers. Not more, not less, exactly. Boom. And 5% chance. So we have a 5% chance of making our quota this month. Let's hope. Part C. All right. What if the question is, what if, we only have 48 phones left for purchase. And we don't want the customers to come in, get a bad, don't get a bad customer service. That is, to come in, they don't get the product, they go to Yelp, they go to Twitter, all right, and we get killed on social media because we don't have it. We have 48 phones left to get us through the night. We know we have 120 shoppers coming in. What are the odds we get through the night? So, again, I build my set. I think about this. Less than 48 shoppers. So that's 47, 46, ... all the way down to 0. Got it. That's awesome for a binom dist. A binom.dist, equals. If you don't do the equals, it doesn't do anything. Binom.dist is great when you need to count down. Tell me the number you want me to start counting at, the set number, that's why I do the set. Tell me how many trials we have so we can set up the formula, 120. Tell me the probability of success, 0.48, and tell me if you want me to count down. That's what the 1 does. When your set goes from blah down to 0, it's time to turn on the counter. Oh, yeah. Uh-oh, we better be ready for some bad reviews. Only 3% chance of this happening. Wow. Again, we're making important practical decisions based on odds because we know it's binomial. And that's what this is all about. All right. A cool one. Really pause right now and see if you can do this without me. We haven't done it between yet. I'm trying to see if you can do this without me. And I'm back. So between, here's what I would do. All right, and including endpoints. Including. So again, I like to do my set. Including endpoints. So that's 62, 61, ... down to 52 because we're including the endpoints. You really got to know if you want or do not want the endpoints. All right, a between is always the subtraction of two distributions. I don't care which one you're looking at below there. Binomial, Poisson, hypergeometric, normal, exponential. It's always done the same way. Less than, straight up the distribution. More than, 1 minus the distribution. Between, subtraction of the two. It's always the same, no matter what distribution you do. All right, instead of binom.dist, using another .dist. That's the cool thing. Once you learn one, the rest fall into place. So in this case, here's what I'm going to do. Binom.dist. I'm going to start at 52 and count down. Please understand that's a problem. Please understand why that's a problem. And that's because when you turn on, and that's why there needs to be a minus, when you turn on the counter, you can't turn it off. Now, yes, I know there's another different binomial on this Excel. I'm not going that way. I'm trying to teach you something. I'm trying to teach you about logic right now. Binom.dist counts down. It counts down from 52. Sorry, realized a mistake. Uh-oh, we're going to be in Excel hell if I'm not careful. I call it Excel hell if you make a mistake. I want not 52, so I apologize. You want the big number, 62. Why is that an issue? Well, because when you count down from 62, it includes numbers below 52, and that's the issue. When you turn on the counter from 62, it goes down to 0. Uh-oh, that's too many people you've included. The minus in set theory is get rid of things you don't want. So that's what I'm doing is, wait a minute, dude, you counted too many. You counted 51 and below. I don't want 51 and below. Get rid of 51 and below. And that's really the way I look at this is I have the ones I want, 62 down to 0. No, 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 no. Get rid of minus, set logic. Get rid of the 51 and 0. If you have 62 to 0, 51 to 0, and you get rid of the 51 to 0, you really only have 62 to 52. Beautiful. Welcome to set logic. Pausing so you guys get a chance, or pause the video so you can see the formula. Beautiful. And there's your odds. Almost 0. I mean, this is a really small number. I can't state that enough. E negative 23 means move this decimal 23 spaces to the left. Really small odds, all right? The really small odds we're going to see between that number of customers. So if we're hoping to see that many, we're in trouble. You might as well be looking for a new job if that's what we were trying to do. All right. We're binomial. That means the expected number is easy peasy lemon squeezy. Tell me n, tell me pi, and booyah. That's the typical number of customers. Typical number is right there. We expect about 58 customers. All right. We truly do expect about 58 customers in this store. 57.6. This is a great moment to say, sometimes Dr. McCullum makes mistakes, and I made a mistake here. I know that hurts you guys when you're doing the video, but it also is important to show you sometimes we make mistakes. Of course, if you're a good class, you're raising your hands going, hey, you made a mistake, you made a mistake. I apologize. I apologize for this big time. What was my mistake? I'm going to stop right there. Come on now. What was my mistake? My mistake is, come on, where's the 300? That was the previous question. I'm using the previous n. Our n is 120 here. The reason I caught my mistake is looking at the expected number 58, and that 58's been between these two. The fact that 58 is typical, that means the odds of this should be pretty darn high. If my typical amount is inside the interval I'm looking at, I expect a pretty big number. That's better. All right, that's a pretty big number, and that is expected. Think about this again. The average number from the previous discussion, that's your average, okay? And in fact, once I have the spread, part F, once I have the spread, I'll even know even better. The spread is the square root of n, this time do it right, pi, and 1 minus pi from our formula again. Just looking at the formula for binomial. Gotta make sure I do it right. Boom. And this would be the per person difference. Or I shouldn't say per person, per group difference. Because we're looking at groups of 120 shoppers. That's really what we're doing is we're counting, here's 120 shoppers right now. How many will buy the phone? Typically 57.6 out of that group of 120. God, that group's gone. Another 120 come into the store. Typically 57.6 buy the product. Got it. Now, when I look at one group to another group to another group to another group, what's the difference between group? What is usually the difference between group? The difference is about 5.47 customers is the difference. So I know I can range anywhere plus or minus 5 on this one. Plus or minus 5 on this one gives me that number if I'm looking at that correctly. So this interval right here should have been really packed with odds, 68%. That makes sense to me because again, I look at this. The typical number is 57 with a plus or minus 5.4. That means, and that's roughly the right odds. 68% fall within that plus or minus 1. All right, that's the usual number there. 68% of us fall between the plus or minus 1s, as I call it. 1 or minus 1 on the standard deviation. Let me just check to make sure I didn't use 300 before. Good. These all say 120. So these are all accurate. Again, I do apologize for that. They're all correct now, and I'm happy. That's the main thing, is all these I want to be correct when you're utilizing my videos. All right, guys, thank you for watching the video. Stay tuned for future ones.